Welcome to this mini lecture on glacial ecosystems. My name is Guillaume Lamarche-Gagnon. I'm a researcher here at the IC3 Research Center based at the Arctic University of Norway. And now we start with a simple definition of what a glacier is. It really is just a body of ice that has accumulated over the years, snow becoming firn, becoming ice, and accumulated enough mass that it is flowing under its own weight. And have different sizes and shapes of glaciers. You can find glaciers terminating on land, called land-terminating glaciers, like the one we can see at the top here. If they terminate in the sea, we call them marine terminating glacier, like the one at the bottom. And glaciers can grow, and we'll refer to them with slightly different terms. For the sake of this lecture, they can be interchangeable. But an ice cap, for example, which is bigger, and then at the larger scale, we define them as ice sheets. At the moment, we have two ice sheets on Earth. So one in the Arctic, which is called the Greenland ice sheet, and the other one in the Antarctic, the South Pole down here. And collectively, these glacial ice masses roughly cover about 11% of the Earth's surface. It's always good to remember as well that most of the fresh water on Earth is contained within these glacial ice masses. And lastly, it's not the coverage of glaciers have changes over time. If we think previous time periods over Earth history, we'd have more or less glaciation. For example, during the last glacial maximum here. Now, for a long time, people were mostly interested in the physical component of glaciers. They thought they might be biologically dead and chemically inert. So we knew they were changing landforms through erosion, contributing to sea level. But we now know, at least on Earth, wherever you find water, you normally find life. And glaciers are no exception. Liquid water. And if you're thinking about liquid water and glaciers, the first place you might be looking at is during the summer, when these systems are melting. For example, the glacial river at the bottom, here, or what we called a supraglacial river on the surface of the ice, like the top photos, which in this case is located on the surface of the Greenland ice sheet. The other thing you might notice from this surface photo is how dark the ice is. And so this is caused due to a variety of factors. So we think about mineral deposition, dust. But also if you take a closer look, you can find that microbial cells make up a significant component of these glacial surfaces in some cases. So having a closer look here, one of the first microbial habitat that you find on a glacial surface walking around are the so-called cryoconite holes. And these holes are formed due to the dark color on these dust and mineral particles, but also the dark pigment on these microbes, which will trap solar radiation, resulting in local melting. And in these trapped little microenvironments, microbes can derive energy and carbon from deposited mineral dust, but also take advantage of this solar radiation, sometimes 24-hour sunlight. And microbes such as cyanobacteria can make up a large component of these environments, fixing nitrogen and carbon dioxide. Another type of microbe that has gained prominence when you look at glacial surfaces in the last decade or so are these so-called glacial algae. And these glacial algae, like the one on the picture here, can have very dark pigmentation, sometimes brown, sometimes black, sometimes purple. And we're interested in those glacial algae because they are making these pigments to protect themselves from the strong UV radiation that you can find at high latitude and high altitude. As a result of this, it's like this black carbon or these black dust that we just talked about, these glacial algae can melt their surrounding ice surface. So if we're zooming out a little bit here and look at the top satellite image, we have a very good look at this dark band margin of the Greenland ice sheet. And we now know that as the summer progresses, this band will become darker and darker. And a large reason will become of this growth, this blooming of these glacial algae that are growing on the ice surface. And they're not only growing, but they will actually contribute to the melting of the ice due to their pigmentation, a phenomenon we call bioalbedo effect, and sometimes up to large component of the melt. And therefore, this is an example where we still have this active ecosystem can have impact beyond the glacial surface. But let's leave the surface for now and follow the water. I used to think, before working in glacial environments, that most of what we find on the glacial surface, the water, will just exit the surface from the top, running off the ice. In fact, what we know is most surface melt on a glacier will exit from below, as depicted on this image here at the top. So water will infiltrate cracks, crevasses, moulins on the ice surface, make their way all the way to the bottom, a place we call the bed of the glacier, or the subglacial environment, interact with whatever is present down there, sediments, minerals, and being exported at the glacial front in the form of a proglacial river, such as the one on the bottom photos. Another thing you might notice when looking at this water is a color differences between the previous slide, a clear meltwater on the surface and a very dark brown, sometimes gray water coming out. And this is caused because of the high suspended sediment load present in this water. And these sediments are coming from this movement of the ice we talked about earlier. Glacier will erode the bedrock and soil underneath, releasing very fine sediment particle, often called glacial flour. And these can be suspended and being exported at the glacial front. And we'll come back to this glacial flour a bit later on. And another nice thing about those rivers is they can offer an indirect access to the subglacial systems. So scientists that would like to study phenomenon happening beneath the ice, they don't necessarily have to first go under the ice or drill through the ice, but they can use these rivers as an indirect window to whatever might be happening chemically or biologically. But what about winter month? What about regions of ices that don't not influenced by surface melting? Can we find liquid water there as well? And we now know that indeed, yes. In fact, large areas of bed of glaciers and ice sheets are what we call above the temperature melting point of water, which means that we find liquid water, wetlands at the base of these ice masses. So on the picture on the right, we can see what we think is present beneath the Greenland ice sheet, and everything in red are regions that would be melted, so the presence of liquid water. And the same is happening in Antarctica and other glacial masses. And this water remains liquid due to local geothermal heat flux, the sheer mass of the ice, and insulation from the core temperatures, but also, again, this movement that creates friction and heat. But not only we have small films of liquid water, we also know that many of these ice masses overlay what we call subglacial lakes. So many hundreds are found in Antarctica. We're discovering more and more in Greenland, and in fact, again, beneath most large ice masses. And these subglacial lakes, we now know, are not just isolated systems, but are connected hydrologically beneath kilometers of ice sometimes, through rivers. They fill and they drain. Therefore, we have an exchange of material that is happening in this hidden world. And what we might find, you're saying. So if you look at the subglacial environment, the microorganisms cannot rely on photosynthesis. So unless you're in part of these subglacial systems that are connected through this surface melt that we mentioned briefly, the organic matter that is present in subglacial environments is relying on whatever was present before ice inception, before the ice covered whatever landscapes was present. And the older the ice, the older the environment, the more degraded we think this organic matter will be. This will also result in differences in oxygen supply. So again, some oxygen can penetrate with this meltwater. Also, the melting of this ice from below can liberate oxygen from the melted ice. But this oxygen is thought to be quickly consumed by both chemical reactions and microbial reactions. And because of this limited organic carbon, a lot of the microorganisms we find in those ecosystems are what we call chemolithotroph or chemolithoautotroph, relying on chemical energy or mineral energy for growth. So we find a whole variety of microbes, depending on what bedrock and mineral and carbon is present in the ice. Another thing to unpack is that just the activity of these microbes, a bit like what we found on the glacial surface, would impact how they live. So the organic acid generated, the CO2 that they breathe out, will also contribute to dissolving and generating some acids, which can result in them having more access to minerals and nutrients that might be found in the soil or bedrock covered beneath. We often think as iron cycling being important. Iron is quite abundant in bedrocks and a lot of, and even the most abundant mineral iron is pyrite is often found, even in small concentration can have, we think, strong contribution to these environments through oxidation. So again, can consume oxygen, but can also weather more minerals that can then be accessed by microbes. And this can be done both just chemically or also by microbial organisms. And iron can also be coupled to different microbial respirations. And lastly, if you think about deep environments that are no oxygen covered all organic matter, one of the results that you might find is methane production. So you will find this in normal lakes, in deep marine sediments. And I'm sure you might have heard this if you are listening to other lectures on extreme environments. Methane is often mentioned. And the bed of ice sheets and glaciers, I think, are no exceptions. So methane can be generated. And if some oxidant, like oxygen, is present, this methane can also contribute to microbial metabolism through oxidation. And the picture on the right just summarizes some expeditions done in Antarctica where they drill through kilometers of ice to cleanly access some of these subglacial lakes we mentioned. And what they found in there is pretty much what we are describing on the left. So a lake with limited oxygen, driving on chemoliths, so inorganic energy sources driving the systems, methane coming from below, et cetera, et cetera. And the realization that subglacial environments might be chemically and biologically active, that they can generate, then use this old organic carbon to produce methane, had made people think whether or not these can have impacts beyond the ice margin. So one of such impacts was potentially this accumulation of methane gas, a potent greenhouse gas, beneath ice caps. Methane can be accumulating over thousands of years, millions of years potentially. And then once the ice melts, all of this greenhouse gas could potentially be released to the atmosphere. We in fact have evidence of this in the northern Atlantic. Some paleo ice sheets that used to cover parts of the marine environments, they left behind these puck marks or these little craters of methane bubbles as methane was degassing. Whether this is happening today beneath Antarctica, we're not sure, but we think we have some environments that might be favorable to promote such subtypes of methane accumulations, but we're not sure. But what about evidence of methane emissions to the atmosphere around glacial margins today? So if we go back on land, back to Greenland, for example, and we go back to these glacial rivers that are exporting subglacial materials and look at what's present in the water, in a lot of these glacial systems, you will indeed find that they are super saturated with this greenhouse gas methane. So this orange curve just shows differences as methane concentration. So this water that has more methane in it than what would be expected if it was just equilibrating with the atmosphere. And the ups and the down corresponds to flushing due to the more or less meltwater entering the system and exporting this microbial methane. And now we have increasing evidence that this is happening worldwide. So in Greenland, Iceland, Svalbard, some glaciers, in the Canadian Arctic, for example, this is happening. So we don't know how important it is yet. It's not happening everywhere, but this is certainly an active area of research. And we need to know more about this. And lastly, I just want to mention another things that I think kind of is gaining attention in the last decade or so. And this is, we're sticking with those sediments, this glacial flour, and looking at those as potential energy supplies for these somewhat isolated worlds beneath glaciers and ice sheets. So we already knew that grinding this rock would create highly reactive particles. So the higher the surface area, the more easily chemical and microbes can attack the surface and extract nutrients and energy. Just breaking some rocks by pressure can also liberate some traps nutrients. So fluid inclusions in minerals can contain bioavailable carbon that can then be accessed by microbes. But the thing that I think is quite cool is this physical erosion, breaking down the rocks, can break down chemical bonds and create what we call free radicals. In this example, we're looking at silicate bedrock, but this is happening in different types of bedrock. And by exposing these free radicals to water, these highly reactive free radicals to water, you can have a bunch of different chemical reactions happen. In this case, we have a generation of, hydrogen gas. So just breaking silicate, reacting with water will create abiotic hydrogen. And we know hydrogen is highly reactive, can be utilized by a range of microorganisms to drive different metabolisms. So here's just this analogy where similarly where you have your wheat, you grind it in flour to make bread, the glaciers can grind the rock to produce flour and liberate energy that can also be consumed. So with this, I would just like to summarize. So I hope that I managed to convince you that glaciers are more than ice and are active ecosystems. Depending on what you look on glaciers, whether that's the surface or the subsurface, you might find different communities that have adapted differently to cope with different extreme conditions. But they're not only surviving in those environments, but they're often thriving, and their metabolism have impact that can go beyond the ice itself. Thank you.